Now, both of these are already posted in the folders. I'm probably going to add some to one of them, and so I'll have to repost it. The first thing to notice is once we start getting into interesting physical integrals, integrate is useful, but unfortunately, it's not super smart. So maybe I want to integrate cosine nx times 1 minus x squared from 0 to 2 pi. I'm not sure why I picked this one, but okay. One of the things you should notice is we know something about sine of 2n pi, which is what? If n is an integer, what is it? Sine 2n pi with n being an integer is 0. But Mathematica didn't get rid of it for me. I also know cosine of 2n pi for n being an integer is 1. I'd like to be able to get rid of those. And that's one of the things when you do integrals in Mathematica, you want to pay attention to your answer. You want to remember enough about functions and integrals and things that you're doing that you can catch things like this. I like to say Mathematica changes the math we do, but it doesn't eliminate your need to think, unfortunately. Now, for simple cases, what you get to do is type the assumptions, and assumptions is something that you can use in lots of places. Now, unfortunately, with this particular case, because of the way it does the order, it doesn't, telling n is an integer doesn't really help, because it's not relevant until after the integral is done, if that makes sense. So it doesn't, there's nothing about doing this integral that knowing n is an integer that helps. It's only when it's all done. You can try simplify. That also didn't do anything. But if I take this integral and wrap it in assuming, now I get what I want. Because what it's assuming being on the outside is that ultimate last step. Right? We've gone from, okay, let's do the integral and then do assuming. I think I forgot to test before class. Yeah, and that's the same thing. If notice by doing the assumptions with my simplify command, it's doing that assumption on the final result from the integral, not the integral itself, and so that works as well. So simplify doesn't know to assume n's an integer, but if I tell it to simplify assuming m's an integer. So one of the things to keep in mind, I always get confused, except in the middle of when I'm teaching the class and I've just looked it up, whether the word assumptions goes on the inside and assuming is on the outside, or the other way around. But so that's one thing, you know, you can always look it up if you're not sure. But that's a key thing to know, and we'll show it again with some other integrals later. But that's particularly powerful when doing Fourier series because of the fact that integers matter. The other thing you need to know is that built into Mathematica, the Fourier series command just by default does the exponential. And I'm pretty sure from minus pi to pi. Now, there are a whole bunch of settings you can give it that, to be honest, I've never completely figured out. So if you have some strange interval, you give it some extra settings, and then it works, and it's like complicated math, and you have A and B, and I don't like it. To be honest, unless I'm doing a simple Fourier series, I use my own, just because it's so easy to write a short little function, which we'll show you later, to get the coefficients and then sum the coefficients times your functions. I do that. But in working with Fourier series and Fourier transforms, we do like to go between our exponentials and our trigs. And so exponential to trig is a great function to keep in mind. And it converts this thing into a cosine 1. And what we see is something interesting. That's about the Fourier series. What do you notice about the Fourier series of 1 plus x squared when you write it in terms of sines and cosines?
It's only cosines.
It's only cosines. Why? It's an even function. So one of the things to keep in mind is that the sine and cosine expansions can be very useful if you know your function's even or odd, because they're even or odd. So cosine is even, sine is odd. So if the function's even, you only can get cosines. Now, I'm going to show you lots of different ways you can do this by hand. Notice in this Mathematica command, what am I doing? Because I just want to show you a bunch of different Mathematica commands. I'm making a table. I'm assuming that n is an element of the integers using the element command. Notice before I was doing it with the element symbol. So I've done it both ways for you, depending which you're more comfortable with. So element n is an integer. I'm going to integrate cosine nx times my function from minus pi to pi. Notice doing it this way, I don't have my normalization. Oh no, there's my 1 over pi. I'm putting my whole 1 over pi with the cosine nx. I'm doing it kind of the book way in this one, because here's my 1 over pi. Notice one of the things that is weird, okay, in this structure that I set up, is you do have to pay attention sometimes with doing tables. Sometimes they work without changing your variable, but sometimes if it's a variable you're using to do a bunch of stuff, it works best to, at the end of everything, use your slash dot, turn it to another variable, and use that as your 1 to sum your table over. So notice I have this strange thing at the end, slash dot, n goes to 1. Let me see if this is a case where I need to do that. No, I didn't need to do it. I just wanted to show you. There will be times where if you do this by itself, notice I'm just picking n from 1 to 4 to generate my table. Some of the expressions in there, this will not behave the way you want. And to make it behave the way you want, you can always change your variable that you're doing everything over with the replace command.
Is that just because you may have defined n several times?
Yeah, it also depends what function and what actions you're doing. Weird things can happen to n. It's most common. How many of you have played with this command? I haven't shown it yet. There's a command manipulate, which allows you to create an active window where you can change your parameters. It's really good for plotting, so you can see lots of different plots. That's one where often you need to do the slash dot at the end to make the manipulate work. And some of these things are left over from the fact that I first taught this course in version 6, so they've gotten better. So the odds that you need to do this are probably less now. So now if I want to make my series, notice this is one way to do it. I'm doing the 0 term separately, because that's just the integral, the average of the function divided by 2 pi. And then I'm creating my sum by taking my coefficients that I made up there and multiplying them by cosine ix. So this one here looks just like the book. If you were following the book's formulas, this is what you would do. And then you get this series, which, if you look up there, matches the one I generated up there. And even cooler, if I plot them together, my Fourier series, which one is the Fourier series, do you think, the red or the blue? The blue, the one that kind of tails off at the top, right? It's a little wiggly because it's all cosines, but it works. Now, there's various ways in Mathematica. This is something that you'll be asked to do in the homework to make things piecewise. One is to just use the command piecewise. So I am now putting together 1 plus x squared, and then I shifted by 2 pi, so I have 1 plus the quantity x plus 2 pi squared. And I'm doing it from minus 3 pi to minus pi, and then I'm doing it from minus pi to pi. And notice my approximation. So this is one of the things that's really cool. The Fourier series, if my linear vector space was periodic, so I'm using periodic functions, is inherently periodic. That's why it curves over a little bit at the top. Because when you cut it at a corner, a sharp point is hard to match exactly. You need to do more and more terms to match it. But notice when I did the plot, I don't have to make g piecewise. Right? G just already is a function that's highly periodic. So if I stick in here, plot g, and I go from, I don't know, minus 4 pi, whoops, minus 4 pi, oh, let's go from 6, well, not 46, 6 pi to 6 pi. Oh wait, why did it stop it? Oh, I'm playing the wrong one. I'm plotting g. I want to plot my Fourier transform. So the Fourier transform, it's just a function of x. So it exists for all x, and it's periodic. That's what it means for my linear vector space to be periodic. Now the Fourier series, even if your linear vector space, say you're doing it for f of 0 equals f of a equals 0, it's still going to assume you meant that to be periodic. Because right, you'll just get a function of x, and it won't know any better. It'll be sines and cosines are periodic. So that is something to keep in mind when you do the piecewise ones. The real function, you have to make periodic by repeating it piecewise. The Fourier series will automatically do it for you. Any questions on that? Because that's a little different. And if any of these things you feel you want me to draw or do something more for, just let me know. Now, actually this I'm going to take a second to draw. What we just did was the function f of x equals 1 plus x squared from minus pi to pi. And then we thought of it by chopping off the pieces that are past there as a periodic function because we only defined it on that range, and we imagined everywhere else it repeats. And more importantly, it's clearly an even function because it's, right, f of minus x equals f of x. Now imagine I take just the piece of 1 plus x squared from 0 to 2 pi. And now if I'm going to make it repeat, it'll do that. Okay. And it's not an even function anymore. So something strange is going to have to happen. What's the first thing that has to happen? I'm going to need some signs to come in. So let's look at that. So now I redo my coefficients. I'm going to make some sign coefficients. And the first thing I notice is they're not 0. If I had done this from minus pi to pi, these would all be 0. So here's my sine nx. There's my cosine nx. So now I'm going to make an approximation that just has the cosine terms like I did before. And if I plot it, you can see it doesn't do very well. Right? These are my cosine terms. This is my function. I mean, first of all, we know cosine of 0 is what? 1. So I'm not going to get this very well. I'm going to have a whole bunch of 1s adding up, no matter what I do. But now, I add in my sine terms, and voila. Now, I still have a bit of a problem here. Why? Because the sine's just 0, so it hasn't helped my 1's. But what is the function trying to do? What does it think is just on the other side of this? The 1, right? It's trying to match 2 points at this point. This is what we call like a Dirichlet condition, or a jump, right? There's a jump in my function. Okay, so even though I made my function periodic, it's not really, really periodic, because f of 0 doesn't equal f of 2 pi. So I made my function periodic, but in a weird way, by having a jump or a step at the boundary. So it's not a great, it's not really in my linear vector space, so this really isn't a basis for it, so it's going to have trouble at those corners. And this becomes obvious when I do the piecewise case. It's actually treating it as going from here to here and thinking of it as periodic, where it's saying, okay, it's really 0 at 2 pi. Or it's really 1 at 0, whichever one you want to think of it as. And that's what it's trying to do. Does that make some sense? So again, I think when we think of these things as these linear vector spaces, then when we do these weird periodic functions that have jumps, we have a better understanding of what's going on. I mean, a common thing to do, for instance, is to do the Fourier series for, step pulses. And again, that's a little better. We can kind of say it is periodic because the value is 1 and 1 at the beginning and the end, but really the value is also 0 and 0 at the beginning and the end. So it's periodic, but in a weird way. F of 0 doesn't, f of, say, A doesn't quite equal f of B. Now,
So what you're saying is if that happens, we've made.
well, the Fourier series basically works still, because it is kind of periodic in a real way, but you have to deal with this discontinuity. It's periodic because you stuck a discontinuity here. You might want to think of it as you don't include 2 pi, really, and maybe the value is a half here and here. Right? So the function is 1 plus x squared on the open interval from 0 to 2 pi, and f of 0 is a half, and f of 2 pi is a half. And now you've formally made it not continuous, but you've made it officially periodic, and that's really what you're doing. And you can ignore those 2 points because they're single points, and you can treat it as going from 0 to 2 pi. You can do everything formally as if it's periodic. Does that?
So I was just wondering, like if this comes up in a situation like trying to analyze what that means, like so does that mean like we didn't plot it effectively, we didn't choose the right linear vector space, or?
No, we basically, discontinuities are hard to match with a finite series is all it's saying, okay, at the end of the day. But you do want to be aware, one reason you can understand that discontinuities are hard to match is that the linear vector space is weird. So the cosines and sines as a basis have weird behavior at the boundaries.